Woohoo, we are live. And this is a conversation about triangles, specifically right triangles, and the Pythagorean theorem, or as I was told to pronounce it by some Greek friends, the Pythagorean theorem. So, Pythagoras or Pythagoras of Samos, and we're talking 500 years before the Common Era, was a Greek philosopher and a mathematician. He founded a whole society that was based on secrecy. They lived in a commune, they were all vegetarians. He had some really interesting ideas about math, and he is credited with a concept called the Pythagorean theorem, or again, the Pythagorean theorem, depending. And so we want to talk about that today because it's a really powerful theorem. So to start off with, we need to talk about right triangles. Now, right triangles are not the opposite of wrong triangles, although that would be fun if you had wrong triangles. I'm not sure what a wrong triangle would look like. I'm sure we could come up with something though. But a right triangle is a special kind of triangle. In general, if you've got just a generic triangle, you basically labeled it as side one, side two, and side three. You've got three sides, three angles. It's literally a tri or three angle. And in the case of a regular triangle, there isn't actually a lot we can say. What we can say is that the perimeter, that's the distance all the way around. So if we go all the way around a triangle, is just the sum of the sides. We can also say that the area of any triangle is equal to 1/2 the base times the height. Now, we're not going to focus on that here because that is a whole lecture on itself. Depending on how the triangle is oriented, you can actually look at different possible bases and different possible heights. And the really cool thing is the area stays consistent no matter how you turn the triangle around. We also know that the sum of the measures of the three angles equals 180 degrees. So angle 1 plus angle 2 plus angle 3 is 180, which is a really useful fact about triangles. Although, again, if you're working with the Pythagorean theorem, we're not going to be working so much with angles, but these are still good things to know. And then each angle and side corresponds in a special way. And a lot of people find this unusual at first. If we look at side one over here, we're going to associate it with the angle that's across from it. So the angle over here. Side two, which is right here, is associated with this angle. And side three is associated with this angle. So if I were to color these sides in, here's this blue side. This is associated with that angle there. See, I need a green. This side of the triangle is associated with that angle. And then this side right here, because I don't have a red highlighter, I have a pink one though, is associated with that angle. Now, if you've taken geometry, you know that I should be using different numbers of lines. What does that mean? Well, so for angle 2, I should probably write the angle in like that so it's distinct from angle 1. Angle 1 has just one little roundy guy there. Angle 2, I'm identifying it with 2. And then angle 3, just to keep the pattern, I will use 3. And that way, just looking at it, even if you couldn't see the colors, you can tell these three angles are different. We're not assuring us. We're not insisting that all three angles are equal, although they could be. If the three angles are equal, you get something called an equilateral triangle. If two of the sides, which means two of the angles, are equal, you've got an isosceles triangle. You got lots of things we could be working with. But what we're really interested in is a right triangle. A right triangle is a triangle with this little boxy guy in one of the corners. And the little boxy guy, the little square in the corner, means 90 degrees. It means it's a right angle. So that angle right there, this angle, let's see, how do I denote it? Right there, that's the right angle, right there. In a right triangle, the sides are usually labeled. They don't have to be. Your book says they're always, and I don't think they're always. Mathematicians don't follow directions, so they're labeled all sorts of things. But frequently, we use the letters A, B, and C, where C is the way we label the side opposite the right angle, and that is known as the hypotenuse. So the hypotenuse, I've colored myself into a corner here. See what I did? What do you think, Bat Brothers? Yes, the hypotenuse, side C, is the longest side. That is the side opposite the right angle. So what's going on here? Well, first off, I've said a bunch of stuff, and if you haven't been reading this, you just heard, I mean, you might need to take a break, sit down, let your brain cool down a bit. But let me turn this paper over and use my bat friends to explain something. If I look at angles as being created by effectively two lines. Now, these are not infinite, so they're not lines, they're line segments, but imagine they go on. The bats could fly forever. Why does it make sense to associate the angle with the side opposite and vice versa? Well, let's look at this. If I draw, I imagine doing this, but I didn't realize chopsticks not the easiest thing to use. Okay, so if I draw a triangle with a relatively small angle here, the side opposite will be relatively small. Now, if I go ahead and I spread out my angle here, so it's a bigger angle, notice that the side opposite, so small angle, leads to a small side. Large angle, large side. So the idea is when my angle is small, the bats aren't very far away. But the wider the angle, the further apart the bats get. Now, obviously, there are other considerations. For example, I could make a much smaller side if I connected right here. Same angle, right? So there are all these third sides I could draw in that could go across there or across there or across there. The point being, if these two are are fixed, they don't change, and I increase my angle, then the distance between the bats gets bigger. So that's why we associate an angle with the side opposite. That's all. Woohoo! Okay, so what the heck is the Pythagorean Theorem? Ooh, it's very exciting. Are you guys excited? I'm so excited. So, along with being something that many students have trouble spelling, which, you know, it's a thing, the Pythagorean Theorem is a very cool and amazing theorem. And the thing that boggles my mind is that this is an association. This association is that the leg, one of the legs, A squared, plus B, the length of the second leg, squared, equals, so the sum of the squares of those two legs equals the square of the hypotenuse. The fact that somebody 500 years before the Common Era came up with this and had figured that it was standard, it was true for all triangles, not just one or two, but that he figured out it was all of them. That's amazing. This is really amazing to me. Now, some people will want to impress you by writing it out. So what does it look like written out? Well, I could say the sum of the squares, so that just means squares, of the legs, right? So this is a leg, this is a leg, this is a leg, and this is the hypotenuse, is equal to the square of the hypotenuse. Bam. The sum of the squares of the legs is equal to the square of the hypotenuse. So you can make it sound all fancy. It doesn't have to be that fancy though. A squared plus B squared equals C squared. This is really cool. So let's take a look at some examples. Like, what could we do with this? Well, it's a good question. If the legs of a right triangle measure 3 feet and 4 feet respectively, what is the length of the hypotenuse? Okay, pretty straightforward. I've conveniently already got my right triangle written out. Now, I have to apologize because I was doing this with Microsoft Word and it only lets me draw a certain shape of triangle. So when I write that this is 3 feet and this is 4 feet, you're going to notice, wait a minute, they look not like 3 feet and 4 feet. In fact, they look like they're almost identical. I apologize. So I'm going to have to write the magic words. Here's my magic words, not to scale. Woohoo! So we want to know what the length of the hypotenuse is. So I'm going to say, okay, this will be A, and this will be B, and this will be C. Sometimes people will try to convince you that A and B have particular positions. They don't. One of them is A, one of them is B. If you want to make A always be the short one and B is always the long one, awesome. If you want to reverse that, it will still work. So I've got A squared plus B squared equals C squared. Okay, so A squared is 3 squared. Remember that when we're doing algebra or even arithmetic, we leave the units out. So I'm just going to write 3 squared plus 4 squared equals C squared. I don't know what that is. So 3 squared is 9 plus 4 squared is 16. Okay. 9 plus 16, that's 25. If 25 equals C squared, what does C equal? Well, technically speaking, depending on what you have studied before you're watching this video right now, you will either give me one of two answers. One answer might be that you say, oh, C is 5, we're done. Or you might say C could be 5 or -5, which is absolutely true. Technically speaking, for the algebra, C could be -5. But can we have the length of a triangle or length of a leg or a hypotenuse of the triangle equal to -5? Not in this dimension, just not going to happen. So I'm going to cross that out. So then my answer is that C equals 5, and then go back to units. These are feet, so it's 5 feet. Ooh. And let's double check. I said the hypotenuse will always be the longest side of a triangle. I got 3 feet, I got 4 feet, and 5 feet is the hypotenuse. It's the longest one. Woohoo, we did it. Yay. How do you think, Godzilla? Godzilla's very impressed. Yay. Okay, let's go on. If one leg of a right triangle, I got my right triangle, measures 7 meters, and the hypotenuse measures 10 meters. Okay, so this is 7 meters. Could I have chosen this one? Absolutely. Doesn't matter. And this is 10 meters. How long is the other leg? Well, I'm going to call this B. I don't know what B is. And then I'm going to set up my equation. This one's A. This one's C. So I've got A squared plus B squared equals C squared. And again, A and B can be reversed if you prefer. I've got 7 squared. I don't know what B is. And I know that C is 10 squared. Okay, so 7 squared is 49 plus B squared equals 100. So far, so good. And I'm going to subtract 49 from both sides. So b squared has to equal 51. And again, depending on what classes you've taken ahead of time, you may have some thoughts about this. Technically speaking, we know that b has to be positive because it's a measurement, it's the length. We don't have negative lengths in this dimension, at least. So when I look at what b is, I can either look at plus or minus, or I can simply look at the positive. But I've got radical 51. Now, it could be that the answer that your problem is looking for, because we know that it can't be negative, because it's a length. I always want to put so much in the corner. So I've got radical or square root of 51, or calculator. So on my calculator, I have, now my particular calculator has a, I don't know if you can see it, a square root key or a radical key right above my x squared. So I'm going to use that. But to use it, I have to use the second and then the x squared. And that gives me, I don't know if you guys can see it, that little square root key. Can you see it? Move this down a little bit. And then 51. And I get, it's approximately 7.141428 and some other stuff. And so this problem doesn't say how to round the answer. So it could be that what it wants is the radical 51. And notice I didn't leave any room. So I'm going to sneak in a little m there for meters. Always include your units. Or this. Or I know someone's very excited about including units. My cats get very invested in my math. Or let's go ahead and round to 2 decimal places, 7.14 meters. So we've got the exact answer here, radical 51 or square root of 51, or the approximate answer, which is just a little bit over 7 meters. Now, let's double check. Is the hypotenuse still the longest one? Yes, quite a lot longer, actually. This one's 7. This is a little over 7. This one's 10. So, woohoo! Okay, so there's another use of the Pythagorean theorem. And the last thing I want to talk about is this really cool idea. And there isn't a problem involved. I just wanted to point it out because this I've always thought was cool. And so hopefully you all think it's cool. Godzilla thinks it's cool. He's going to show up for this. But there's the concept in math of Pythagorean or Pythagorean triples. So a triple is a set of 3 numbers. And these are 3 numbers that satisfy the Pythagorean theorem. And I know this is teeny tiny if you're watching the video. So let me show you one possibility. The triple is 3, 4, 5. Now we saw this right here, 3, 4, and C was 5. So if I take a look at it again, 3 squared plus 4 squared equals 9 plus 16, which equals 25, which is, yay, 5 squared. So 3, 4, 5, 3, 4, 5 is a pattern. It satisfies the Pythagorean theorem. Okay, what about another one? 5, 12, 13. Well, now this one you may need a calculator for. 5 squared plus 12 squared. Hopefully you have these memorized. So 5 squared is 25. 12 squared is a gross. It's 144. I know it's a funny word, gross. But that's not what that means. It means it's just the description of the fact that it's 12 sets of 12. 25 plus 144, I happen to know is 169, which I just happen to know is 13 squared. So 5 squared plus 12 squared equals 13 squared. So I've written down, let's see, 4 of them here, 5, 12, 13, 6, 8, 10, 7, 24, 25. If you're in the middle of a set of homework where you're working with Pythagorean theorem, you're going to see those numbers show up a lot because these are the numbers we can use to give you exact values on your triangle. For example, I'm free-handing this, and I apologize again, not To scale. Magic words. Abracadabra, not to scale. But I can go ahead and now if I had the Pythagorean theorem 6, 8, 10, I know which numbers go where because the biggest number is always going to be the hypotenuse. Now the other two numbers, if I write 6 and 8 here, can I convince you? Oh my goodness, I got so excited. My right triangles are just going completely off the rails there. Can I convince you that these two triangles are the same triangle? I know this one says 6 is the standy uppy one and 8 is the lie downy one. And this one says 8 is the standy uppy one and 6 is the lie downy one. But can I convince you that this triangle is just this one sitting in the other way? So it rolled over, like in the middle of the night. And you got to get your foot back under the covers because of, monsters. Yeah, totally. Everybody understands that. Humans understand. Yeah, even Godzilla. Yes. So you roll over, same person though, even if you're upside down. So same triangle. What's the important part? The side opposite the right angle is always going to be the biggest measurement. Woohoo! You guys are awesome. You made it through another questionable video. The Bat Brothers say, woohoo, thank you, yay. I say thank you. Good luck, guys. Have fun with your homework. Math on. Woohoo, math on.